Hello everyone, so welcome to my channel again. So in our previous videos, we already talked about how we can do the linear regression, how we can use the least square estimator to find or decide the value of our parameter beta 0 and beta 1 in the linear regression. So in this video, I will talk about how we can do the hypothesis test for our linear regression. And this is also about the ANOVA. So this is about our variance analysis of our variance approach. So first, let's see, when we try to construct a model of our linear regression, we can write this as y is equal our beta 0 plus beta 1x plus the epsilon. So here epsilon is our error term, and we always assume this one is a normal, a noise, random noise, and it follows a normal distribution with 0 as the mean and the sigma square as the variance. So then, if we want to do a hypothesis test, what do we want to test? So here, in fact, what we want to do is we want to find is this relationship between our x and y follows a linear regression. So in other words, if we draw a graph of our x and y, this means is the slope of our graph is a constant. So if this slope is a constant, like y equal 3 plus 2x, y equal 0 plus 3x, then this means this is a straight line, right? And that's why this is a linear relationship. So here, if we want to check our slope is a constant or not, that means we want to check our parameter beta 1 is a constant or not. So then this is our null hypothesis, our H0. So here we in our previous video, we already say for our null hypothesis, it's always a equation. And for our alternative hypothesis, H1 is will have three cases. Is unequal, greater than, or smaller than. So here, because we want to check this is a linear, or our slope is equal a constant or not. So that's why here for our H0, this is beta 1 equal beta 1 comma 0. So here, previous when we try to test a mean is equal a number, like what we will denote, we say mu equal mu 0, right? So we always use mu sub 0 to show this is some constant number we will plug in when we do some problem. So here, similarly, we also use sub 0 to show this is our assumption or our claim. So here, because we test about the beta 1, so that's why we use beta 1 comma 0. And then for our alternative hypothesis, this will become an inequation. So it's beta 1 is not equal our beta 1 comma 0. So this is our hypothesis here. And then when we want to do a hypothesis test, what should we do? So the first step is we should construct a test statistics. So it maybe follows a normal distribution or follows a t-distribution. So here what we should do is, because we want to test the claim about our beta 1, right? So similarly, we will use the estimator of our beta 1, and then we will construct a test statistic of our beta 1. So here, for our beta 1, what is a notation for our estimator of beta 1? So similarly, we will use the hat to show the estimator of our beta 1. So this is a beta 1 hat. It also follows a normal distribution. So here, because when our original test about the error term, right? We say error term is follows a normal distribution with mean as 0 and the variance as sigma square. So here for our beta 1, estimator of beta 1, so it also follows a normal distribution, but now the mean is the true value of our beta 1, and then the variance is a sigma square divided by S sub double X. So here this S sub double X, we already introduced this in our previous video, but I will also write this here. So this S sub double X is sum from, if we given the data set of our X, then this S sub double X is the sum of the square of each data point minus n times the square of our sample mean X bar. So this is how we can compute this SXX. So when we have this distribution of our beta hat, then of course we can use this one to generate our test. So what we can do is here, when we don't know if we know the true value of our sigma, so we can use this equation to divide it by our minus the true value of our beta, and then divide it by the standard deviation here for this normal distribution. So in other words, let me write down this. We can construct our z-test statistic. So then this means when we claim the null hypothesis is true, so that means we will plug in this beta 1, 0 in our numerator after this minus symbol, and then divided by the standard deviation. So this is the square root of our original normal distribution variance. So here this will become the sigma divided by the square root of our XX. So this one will become a standard normal distribution with 0 and variance as 1. So then what we can do is similar to our previous z-test in our previous videos, and then we can do the z-test to this part. And then this is only true when we know the true value of our sigma. So in other words, if we know the variance of our error term. However, if we don't know the variance of our error term, we don't know what's the true value of sigma, what should we do? So this is, again, we talked about this several times in our previous video. What should we do? We should use the estimator of our sigma to replace the term in our test. But this one, because in this situation, we can now say this is a normal distribution. So in that case, when we don't know the true value of sigma, we should use the t-test instead of a standard normal distribution here. So we will have this one, and we use construct our t-test statistic. So all other terms are exactly same with our z-test. The only difference is here we use the estimator of our sigma hat, to replace the original sigma in the z-test. So now this t-test statistic, this is follows a t-distribution, and the degree of freedom for our t-distribution is n-2 in this case. So then what should we do is here, of course, our other thing is exactly same with our previous t-test. So here, because we can have this is follows a t-2 distribution, so we can find the critical value for this question, because our alternative hypothesis H1 is an inequation. So that means now we do a two-side test. So this means here our critical value will become our T alpha over 2, n-2. And in other words, we will have our critical region. So our critical region is the absolute value of our T0 is greater than our critical value, the T alpha over 2, n-2. So this is how we can do the hypothesis test when we know the true value of the variance for our error term, or if we don't know the true value of our variance for the error term. So now let me give one example here to explain how we can follow or do this hypothesis test when we have some data. So let's look at this question. So now assume this is a data set with 5 pair of data, and then here to show the computation, I already give you some result of the calculation. So we have the S sub XX is equals 32.8, and our estimator of our beta 1 is negative 0.49, and then the estimator of our sigma square is equal 0.72. And in this question, the question asks us to do a hypothesis test of the claim. Is there a linear relationship between our x and y for a given significant level alpha equal 0.05? So here, about this question, if we want to do about this question, the first thing is we should write down what is our hypothesis test here. So of course, for our non-hypothesis test, the H0, this we will write it as an equation. So this is our the beta 1 is equal something. So here our proofers will already say if this is equal some constant or not, we can have this one. So in general, what we will have here, so we will write the beta 1 is equal 0, or beta 1 is not equal 0. So we use this one to test the relationship as a linear relationship or not. So this is our how to decide our hypothesis test. We always use a constant 0 for the linear relationship. And then the next thing is, because in the question, they already give us the estimator of sigma square, right? So that means here we don't know the true value of the variance for the error term. So what we should do is we should construct a t-test. So here, if we want to construct a t-test, then we should plug in the equation here. So here, if we want to plug in the values in our equation of this t-test, so this means we will plug in this beta hat, beta 1 hat. We already have the value is negative 0.49, and then we minus our beta 1 0. So here we use 0 for our linear relationship. And then for the denominator, we should use the estimator of sigma divided by square root of xx. In the question, because they give us the sigma hat square, so that means the sigma hat will be square root of our sigma hat square. So that means this is the square root of 0.72 divided by the square root of our xx. So the value of our xx is 32.8. So this is how we can construct our t-test statistic. And the next thing is just use a calculator to compute this value. So if you use your calculator, you will find the answer of this one is negative 3.31. So this is our value for our t-test, t0. And then the next thing is now what should we do to find this? Should we reject our claim or we should accept it? So for this one, what we should do is we should check the critical value or check the critical region. So to find the critical value or critical region, so they are similar. The thing we should do is we should check the value of our t alpha over 2, comma n minus 2. So here for the alpha, we already have in the question, they given us the significant level alpha equal 0.05. So that means here we just use 0.05 to divide it by 2. So we will use this as 0.025. And then here, because in the original question, they said this is a data set of five pairs data. So that means the value of n should equal 5. So here we should have 5 minus 2. So this is 3. So now we should use the t table to help us find the value of t at the significant value 0.025 for a degree of freedom equals 3. So by the t table, we have the value of this one is equals 3.182. Okay, so this is our critical value. So now what we want to do is we want to find is our T0 inside our critical region or not. So here that means we should compare the absolute value of our T0 to our critical value. So here, because the T0 equal negative 3.31, so the absolute value of our T0 is 3.31. So of course, this one is greater than our T alpha over 2 comma n minus 2. That means this is greater than 3.182. So here, because we have this T absolute value of our T0 is inside our critical larger than our critical value. So that means what should we do? So we should reject our H0. So when we reject the H0, what this means? This means the value of our beta 1 is not equal 0. So in other words, if it's not equal 0, it can equal some other like not 0 value. So here what we will have our x and y has a linear relationship. So this is the result for this question. So now we prove that we should reject our null hypothesis beta 1 equals 0. So that's why we can conclude our x and y have some linear relationship. So this is how we can check about our value for beta 1 to do a test hypothesis test. Then how about the beta 1? How about our beta 0? So we already done beta 1, and now let's move to the beta 0. So for our beta 0, the idea is similar. We still test about our beta 0 is equal or constant or not equal or constant. So that means we still do a two-side test to our for our beta 0. So here. So then the similar thing is by this one, we can still have very similar hypothesis, the null hypothesis and alternative hypothesis. So here we can have these two equations. And the similar thing is also if we have test a beta 0, if we find this is equal 0 as a null hypothesis, and in the future if we cannot reject this, then that means there is no linear relationship. Otherwise, if we can reject the beta 0 equals 0, then they will have a linear relationship. So, and then for this one, of course, the idea is still similar. We construct a test statistics, and then we check the critical value, compare it, find for critical region, and then we can give our compare the T0 or Z0 with our critical value. We can give a conclusion. Should we reject our H0 or we can't to reject it? So then here the only difference is in our beta 1, we say beta 1 is follows a normal distribution with mean as beta 1, and the variance is sigma square over S sub xx. And here in the beta 0, this is a little difference. our beta 0 is still a normal distribution, but the mean and variance is different. So here for our beta 0, of course, the mean is the true value of our beta 0. But here for the variance is a sigma square and times the parentheses 1 over n plus the x bar square. So here this is our sample mean and divided by our s sub double x. So this is our variance. So here you can see this is a little complicated than the variance of our beta 1. So because this one is our distribution of our beta 0, if we don't know the true value of our sigma, so we don't know the true value of the variance of the error term, so then we should use a t-test. So for this t-test, the definition of our t is still similar. It still uses our estimation of beta 0 minus our claim of the constant in our null hypothesis. But the difference is because we still divided by our standard deviation, but because now our beta 0 have a little more complicated variance. So that's why here for this term, we should have this is divided by the square root of sigma hat square times the parentheses 1 over n plus the x bar square divided by s sub double x. So this is a term for our denominator. And now this one is still follows a t n minus 2 distribution. So now you can know this is our t-test. And then the other thing is exactly similar. We still have the critical region and critical value. So because this is a two-size test, so we will have the critical region is t absolute value of our t0 is greater than the t alpha over 2 comma n minus 2. So this is the critical region in this case. So then let's introduce one more test for our hypothesis to check if this xy has a linear relationship or not. So this one we will use the analysis of our variance approach. So in generally in statistics we call this as ANOVA, ANOVA, ANOVA. So for the ANOVA, what we want to do is we want to use the double S, the sum of square we introduced in our previous videos. So if you don't know this, so please look at my video about the simple linear regression. So here I just give a quick equations about what is our 3 double S sum of square here. So I use the purple color for the recall and review part. The first one is our double S sub E. So double S sub E is the sum of square for our error term. So the equation of this is equal the sum of the square of our error. Or if we get the estimator of our y hat, so this is because the error means the difference between the true value or our data set of y and the estimator of y, right? So then this is also equal the sum of the square of our difference between the y and y hat. So this is our double SE, and then we also have two other terms. One is a double ST and double SR. So I also write these two equations here. So for the double ST, this is about our y term. So this is the sum of square of our yi and minus the number of the data pairs n times the square of the sample mean for our y, so y bar. And then this double SR, this is about the beta 1 hat times our S sub xy. And here the S sub xy is equal, let me also write down this equation. It's equal the sum of the product of our x and y and minus the number of the data pairs times the simple mean of x times the simple mean of y. So this is the equation for our sum of squares, the double SE, double ST, and double SR. So based on this definition, of course, we can have a relationship between them. So this relationship is our double SE. This double SE is equal to the difference between our double ST and double SR. So this is a relationship about our residual here, or you say the sum of square here. So then based on this one, what we have in our previous, we also have here for our double ST, we have this degree of freedom, DOF. This DOF is n minus 2. And then for our double SR term, for this term, we will also have this term, the degree of freedom. So here, for degree of freedom here, the degree of freedom is 1. So this is two property of our SST and SSR. And the last thing we can have with this sum of square is if we check about the mean of our double SSE divided by n minus 2. Then the mean of this equation, in fact, is equal our true value of our sigma square. So this is about our double SE, and then about our double SR. And here I just found I have a table in my previous equation. So here about our double ST, the degree of freedom for this one is 1 minus 1. And then for the double SE, this degree of freedom, this is n minus 2. Okay, so now you can see in the left side of our equation and right side of equation, this degree of freedom is also follows the same relationship between our double SE, double ST, and double SR. So it's also n minus 2 is equal n minus 1 minus 1. Okay, so then this is, let us continue on our property for our sum of squares. So here, except the double SE divided by its degree of freedom, for our double SR divided by its degree of freedom, 1. So we have this one, the mean is equal our sigma plus sigma square plus the beta 1 square times S sub XX. Okay, so this is the property for our double SR. So here now we already review the all properties of our sum of squares. And then what we want to do here, we still want to test about our relationship between x, y is a linear or not. Or in other words, we want to test our beta, like beta 1 is equal or constant, for example, 0 or not. If the beta 1 equals 0, it's not a linear relationship. If the beta 1 is not equal to 0, it means everything good, linear. Then in previous, we already talked about the t-test, right? So here what we do is, in fact, instead of a t-test, we can also use our relationship of our sum of squares to do this. So what we have here, we can construct a new test statistics. So here the name of this one is F test statistics. So this is our F test. So here we will construct the test statistic F0 as the numerator is S double SR divided by S degree of freedom as 1 divided by our double SE divided by S degree of freedom. So its degree of freedom is n minus 2. So this is our term for the test F test we have. So then as why this is called as F test, because this follows a new distribution, and this distribution is our F with 2 degrees of freedom. One is about numerator as 1, comma the denominator degree of freedom, so n minus 2. So this is a new distribution here. And also, if you look at any table of the statistics, then we also have the table of this F table. So here, let me write this F1, n minus 2 distribution. So this is a distribution with 1 and n minus 2. Okay, so this is about our degree of freedom. And then what we will do about this test. So here about this test is still about find a critical value of our test, and then, or in other words, find the critical region for our test. So for here about this F distribution, for a given significant level alpha, we will have the critical value or critical region is, we will check the value if our F0 is greater than our critical value, F alpha, 1, n minus 2. So this is our critical region. So in other words, if our F0 is greater than our F alpha, 1, n minus 2, we will reject our H0. Okay, so this is about the ANOVA, or in other words, about the F test. So then let me give a quick example about this part. So here the question is use ANOVA test, or in other words, our F test, to check if this is a linear relationship between our x and y for the given parameter alpha equal 0.05, beta 1 hat equal negative 0.59, and our s sub xy is equal negative 16. And the estimator of our error variance is sigma square hat equal 0.72. So this is the information we have, and we want to do a hypothesis test. So because here in the question we have the estimator of our beta 1, right? So when we check this linear relationship, what we should do is we should construct a hypothesis of our value for beta 1. And also because this is about is a linear relationship or not, so that means we will check our beta 1 is equal 0 or not. So here, let's first, we should write down our hypothesis test, the H0 and H. So we will have this is still this two equation. For the H1, we still have the two-side test, so it's a yin equation here. And then to use our F0, what we should have the value of our SSR, SSE, and here for this question, what we need have here is we need to have our SSR. So here for our SSR, based on our previous one, we already know this equation is the estimator of our beta 1 times S sub xy. So that's why here we only need to plug in our value. So beta 1 hat is negative 0.49 and S sub xy is a negative 16. So just use the calculator, we can compute this answer. Is equals 7.84. So this is the value for our SSR. And then for our SSE divided by the degree of freedom, SSE divided by n minus 2. So here maybe you will ask me a question like, okay, the SSE is a sum of square for our error, and then but we don't know the data points here, the y and y hat. We don't know the error term ei, and we don't know how many data pairs we have in this question. However, if you recall the property of our SSE divided by n minus 1, we know the estimator of this one is equal our sigma, right? So then what we have, in fact, here we can use the estimator about our sigma hat square to use this value for our SSE divided by n minus 2. So that means here for this term, this will equal our equation 0.72. Okay, so now we already have all of the value to use our F test statistic. Numerator is SSR divided by 1, denominator is SSE divided by n minus 2. So here what we have is numerator is just 7.84 divided by 1, and denominator is just 0.72. So then use the calculator, we can get this answer. The answer is 10.8. Okay, so this is our value for F statistic. And then for our critical value, we have this is F alpha, 1, n minus 2. So here in this part, what we need is in this one, we will need pairs or how many pairs, right? So here in this question, in fact, this is also about this. If you look at the data, it's similar with our previous example, right? So for here, for this one, we also have this n is equal 5 here. So that's why here for our critical value is f, and alpha is a 0.05, and value 1 and 3. So then if you look at the table of f table, then we will have this one is equal 10.13. Okay, so now we have this is our critical value. So if we compare of our f0 with our critical value, we will find the 10.8, of course, is greater than our 10.13. So that means we will reject our non-hypothesis H0. And this, in other words, it means our x and y have a relationship, have a linear relationship. So this is a question here. So we already done this part, and here what we do is we always do a two-side test. So for an equation for our H1, and of course if you want to do some one-side test, the idea is very similar for our previous hypothesis test part. All idea is similar, just when you do a t distribution, the t-test, you should, instead of use t sub alpha over 2, you should use t sub alpha. And then for our f-test, in fact, we can now do a one-side test. So when we want to do a one-side test, always use the t-test. Okay, so this is about materials for the hypothesis test for linear regression. In our next videos, we will continue for the linear regression part, but we will move to the confidence interval about the statistical inference. So then please subscribe my channel, and let's see you in my next video.